Close your eyes and imagine standing at the edge of a vast volcanic crater. The air is still and warm. Below you, the ancient rocks tell stories of fire and creation that stretch back millions of years. The volcano is quiet now, sleeping, just as you soon will be. Tonight, we journey through the remarkable world of volcanoes. These mountains of fire have shaped our planet since its earliest days. They have built continents, created islands, and transformed landscapes in ways that still astonish scientists today. There is no test waiting at the end, no rush, no urgency. Just the slow unwinding of geological wonders to carry you gently towards sleep. Volcanoes are among the most powerful forces on Earth, and yet there is something deeply peaceful about contemplating their ancient rhythms. They remind us that change happens slowly, that even the mightiest mountains are patient, that fire, given enough time, becomes stone, and stone becomes soil, and soil becomes life. Tonight, let us explore over 100 peaceful facts about volcanoes, each one shared in a soft voice designed to help you relax, learn, and gently drift into restful sleep. So settle in, let your breathing slow, and let the warmth of the earth carry you toward rest. Welcome to Sleepy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts of distant mountains and ancient fires. Either way, this journey is for you. There is something profoundly calming about contemplating the forces that shape our world. Volcanoes are older than humanity, older than most life on Earth. They were here before us, and they will continue long after we are gone. And yet, we are connected to them. The air we breathe was shaped by volcanic gases. The soil that grows our food was enriched by volcanic minerals. In ways both obvious and hidden, volcanoes have made our existence possible. So let the weight of the day drift away, let your thoughts grow soft, and let us begin our peaceful exploration of the world beneath our feet. The word volcano comes from the name of the Roman god of fire. The ancient Romans believed in a god named Vulcan who ruled over fire and metalworking. They thought he had his forge deep beneath a mountain on the island of Sicily. Whenever Mount Etna erupted, the Romans believed Vulcan was hammering on his anvil, crafting weapons for the other gods. This mythological connection gave us the word we still use today, volcano, a word that carries within it thousands of years of human wonder at the fires that emerge from the earth. Throughout history, people around the world have created stories to explain volcanic eruptions. The Hawaiians spoke of Pele, the goddess of fire who lived in the crater of Kilauea. The Japanese told tales of a giant catfish whose movements caused both earthquakes and eruptions. The Greeks believed that the monster Typhon was imprisoned beneath Mount Etna, and his struggles caused the mountain to smoke and rumble. These stories remind us that volcanoes have always captured human imagination. They are windows into a world normally hidden from view. There are approximately 1,500 active volcanoes on Earth today. Scientists define an active volcano as one that has erupted within the last 10,000 years or shows signs of potential future activity. By this measure, roughly 1,500 volcanoes around the world are considered active. These volcanoes are not distributed evenly across the globe. Most of them are concentrated along the edges of tectonic plates, particularly around the Pacific Ocean in a region known as the Ring of Fire. Others are found at mid-ocean ridges, where plates are pulling apart, or above hotspots, where plumes of hot material rise from deep within the Earth. At any given moment, between 20 and 50 volcanoes are actively erupting somewhere on our planet. Most of these eruptions are small and go unnoticed by anyone except the scientists who monitor them. But occasionally, a large eruption captures the world's attention and reminds us of the power sleeping beneath our feet. The largest volcano on Earth is Mauna Loa in Hawaii. When we measure volcanoes from base to summit, Mauna Loa is the undisputed champion. This massive shield volcano rises from the floor of the Pacific Ocean, where its base sits nearly 5,000 meters below sea level. From there, it climbs to a summit over 4,000 meters above the waves. The total height from base to peak exceeds 9,000 meters, making Mauna Loa taller than Mount Everest when measured from base to peak rather than from sea level. But height is only part of the story. Mauna Loa also covers an enormous area. The volcano spans roughly 5,000 square kilometers, and its volume exceeds 75,000 cubic kilometers. It is so massive that its weight has actually depressed the ocean floor beneath it by several kilometers. Mauna Loa has erupted 33 times since records began in 1843. Most recently, it awakened in late 2022, after nearly 40 years of quiet slumber. The eruption lasted about 2 weeks before the volcano returned to its peaceful slumber. The largest volcano on Earth is Mauna Loa in Hawaii. When we measure volcanoes from base to summit, Mauna Loa is the undisputed champion. This massive shield volcano rises from the floor of the Pacific Ocean, where its base sits nearly 5,000 meters below sea level. From there, it climbs to a summit over 4,000 meters above the waves. The total height from base to peak exceeds 9,000 meters, making Mauna Loa taller than Mount Everest when measured from base to summit rather than from sea level. But height is only part of the story. Mauna Loa also covers an enormous area. The volcano spans roughly 5,000 square kilometers, and its volume exceeds 75,000 cubic kilometers. It is so massive that its weight has actually depressed the ocean floor beneath it by several kilometers. Mauna Loa has erupted 33 times since records began in 1843. Most recently, it awakened in late 2022 after nearly 40 years of quiet. The eruption lasted about 2 weeks before the volcano returned to its peaceful slumber. Volcanoes can create their own lightning. During powerful eruptions, something extraordinary happens in the sky above the volcano. Lightning begins to crackle through the ash cloud, illuminating the darkness with brilliant flashes of electric blue. This phenomenon occurs because the ash and rock fragments ejected during an eruption collide violently within the rising plume. These collisions create electrical charges, similar to how ice particles generate lightning in ordinary thunderstorms. As the charges build and separate, the voltage difference eventually becomes great enough to trigger lightning bolts. Volcanic lightning can be spectacularly beautiful. The bolts dance through clouds of ash, creating displays that seem almost supernatural. Some eruptions have produced thousands of lightning strikes in a single hour, turning the sky into a flickering light show. Scientists call these events dirty thunderstorms. They remain one of the most visually stunning phenomena in all of nature. The deepest known volcano lies beneath the Pacific Ocean. Most of us think of volcanoes as mountains rising above the land, but the majority of Earth's volcanic activity actually occurs on the ocean floor, hidden from view beneath kilometers of seawater. The West Mata volcano sits nearly 4,000 meters below the surface of the Pacific Ocean, near the islands of Fiji and Samoa. In 2009, scientists using remotely operated vehicles observed this volcano actively erupting in the crushing pressure of the deep sea. They watched as lava oozed from vents and explosions sent rock fragments tumbling down the underwater slopes. It was the first time humans had ever witnessed a deep-sea eruption in progress. The discovery reminded us that volcanic activity extends far beyond what we can see from the surface. The ocean floor is covered with volcanic features, most of which remain unexplored and mysterious. Volcanic soil is among the most fertile on Earth. The same eruptions that can devastate landscapes also enrich them over time. Volcanic rocks contain minerals like potassium, phosphorus, and nitrogen that are essential for plant growth. As these rocks weather and break down, they release their nutrients into the soil. This is why some of the most productive agricultural regions in the world are located near volcanoes. The slopes of Mount Vesuvius in Italy have been farmed for thousands of years. The volcanic islands of Indonesia support some of the densest agricultural populations on the planet. The coffee grown on volcanic slopes in Central America and East Africa is prized for its quality. Farmers have always been willing to accept the risks of living near volcanoes in exchange for the exceptional fertility of volcanic soils. It is a bargain that has been struck in countless cultures throughout human history. Lava can reach temperatures exceeding 1,200 degrees Celsius. When molten rock emerges from a volcano, it carries with it the intense heat of the Earth's interior. Fresh basaltic lava typically ranges from 1,000 to 1,200 degrees Celsius, hot enough to glow bright orange or even yellow. At these temperatures, lava can melt most materials it encounters. Steel begins to soften around 1,500 degrees Celsius, so the hottest lavas can damage even metal structures. Concrete, wood, and plastic are destroyed almost instantly on contact. Despite its extreme heat, lava usually moves slowly enough that people can walk away from it. Most lava flows advance at speeds of a few kilometers per hour or less. However, on steep slopes, lava can accelerate dramatically, and some particularly fluid lavas have been known to reach speeds of 60 kilometers per hour. The glow of lava at night is mesmerizing. It pulses with an inner fire, shifting between red and orange as the surface cools and fresh molten material breaks through from beneath. Some volcanoes have been erupting continuously for thousands of years. The island of Stromboli in the Mediterranean Sea holds a remarkable record. This small volcanic island has been erupting almost continuously for over 2,000 years, earning it the nickname the Lighthouse of the Mediterranean. Sailors throughout history have used the glowing summit of Stromboli as a navigational beacon. Every few minutes, the volcano produces small explosions that throw incandescent lava fragments into the air. This steady, rhythmic activity has become so predictable that scientists use the term Strombolian to describe similar eruptions at volcanoes around the world. Stromboli is not the only volcano with a long eruptive history. Kilauea in Hawaii erupted almost continuously from 1983 to 2018, a period of 35 years. Mount Yasser in Vanuatu has been erupting for at least 800 years. These persistent volcanoes remind us that some volcanic activity is not a sudden event, but an ongoing process. The sound of the Krakatoa eruption was heard thousands of kilometers away. On August 27, 1883, the volcanic island of Krakatoa in Indonesia exploded with one of the most powerful eruptions in recorded history. The sound of the explosion traveled across vast distances, reaching places that seem impossibly far away. The eruption was heard clearly in Australia, nearly 3,200 kilometers distant. It was also heard on the island of Rodriguez in the Indian Ocean, almost 4,800 kilometers from Krakatoa. People who heard it reported sounds like distant cannon fire or thunder. Scientists estimate that the sound level near the volcano reached about 170 decibels. At that intensity, sound waves are powerful enough to rupture eardrums. The shock wave from the explosion circled the Earth multiple times, and barometers around the world recorded the pressure changes for days afterward. Krakatoa remains a reminder of the immense power that can be released when a volcano erupts at full force. Volcanic eruptions have changed the course of human history. Throughout the ages, major eruptions have disrupted civilizations, altered climates, and reshaped the political landscape of entire regions. In 1815, Mount Tambora in Indonesia erupted with tremendous force, ejecting so much material into the atmosphere that it blocked sunlight around the world. The following year, 1816, became known as the year without a summer. Crops failed across Europe and North America, food prices soared, famine spread through many regions. Some historians believe the resulting social unrest contributed to political upheavals in the years that followed. Other eruptions have had similarly far-reaching effects. The eruption of Thera around 1500 BCE may have contributed to the decline of the Minoan civilization. The eruption of Laki in Iceland in 1783 caused crop failures that some scholars link to the French Revolution. Volcanic events have shaped human history in ways we are still discovering. Some volcanoes emit blue flames from burning sulfur. At Kawah Ijen volcano in Indonesia, visitors can witness one of the most unusual volcanic phenomena on Earth. At night, brilliant blue flames flicker across the volcanic landscape, creating an otherworldly scene. These flames are not lava, they are burning sulfuric gases that emerge from vents in the volcano. The gases ignite when they reach the air, producing flames that can reach several meters in height. The blue color comes from the combustion of sulfur, which burns with a distinctive azure hue. During the day, the flames are largely invisible, but at night, they transform the volcano into a landscape of dancing blue fire. Miners who work on the volcano, extracting sulfur deposits by hand, navigate this eerie environment as part of their dangerous work. Kawah Ijen also contains one of the world's largest acidic crater lakes. The water is a striking turquoise color, stained by dissolved sulfur and other volcanic compounds. It is a place of strange beauty. The Pacific Ring of Fire contains most of Earth's active volcanoes. Encircling the Pacific Ocean is a horseshoe-shaped zone of intense geological activity. This region, known as the Ring of Fire, stretches from New Zealand through Indonesia, Japan, and Russia, across to Alaska, and down the western coast of the Americas to Chile. Within this zone lie approximately 75% of the world's active volcanoes. The Ring of Fire is also responsible for about 90% of all earthquakes. It is the most geologically restless region on our planet. The Ring of Fire exists because of the intense tectonic activity along the edges of the Pacific Plate. Where this plate meets other plates, one is often forced beneath the other in a process called subduction. As the descending plate reaches the hot mantle below, it releases water that lowers the melting point of surrounding rock. Magma forms and rises toward the surface, creating the volcanoes that dot the Ring of Fire. Living within this zone means accepting a certain level of geological risk, but it also means living in some of the most dynamic and beautiful landscapes on Earth. Volcanic lightning can strike thousands of times during a single eruption. We mentioned earlier that volcanoes can generate their own lightning, but the scale of this phenomenon can be truly astonishing. During the 2010 eruption of Eyjafjallajökull in Iceland, scientists recorded lightning rates as high as several hundred strikes per minute within the ash plume. The 2015 eruption of Calbuco in Chile produced similarly intense electrical activity. These volcanic lightning storms can be far more concentrated than ordinary thunderstorms. The lightning occurs not just near the vent, but throughout the eruption column, which can extend many kilometers into the sky. Different types of volcanic lightning have been identified. Near-vent lightning occurs close to where the material is being ejected. Plume lightning develops higher up as particles continue to collide in the rising column. The electrical displays can last as long as the eruption itself, sometimes continuing for hours or even days. For observers at a safe distance, volcanic lightning is one of the most spectacular natural phenomena on Earth. Obsidian is volcanic glass formed by rapid cooling. When lava cools extremely quickly, there is no time for mineral crystals to grow. Instead, the molten rock solidifies into a smooth, glassy substance called obsidian. Obsidian is typically black, though it can also occur in other colors depending on trace elements and inclusions. Some obsidian shows rainbow-like reflections caused by tiny gas bubbles trapped during cooling. Other varieties display snowflake patterns created by small white crystals of a mineral called cristobolite. Throughout human history, obsidian has been prized for its ability to be shaped into extremely sharp edges. Stone Age peoples around the world used obsidian to make cutting tools, arrowheads, and spear points. The edges of obsidian blades can be sharper than modern surgical steel, and some contemporary surgeons have experimented with obsidian scalpels for delicate procedures. Obsidian is also beautiful. Polished obsidian was used as mirrors in ancient cultures, and it remains popular for jewelry and decorative objects today. Supervolcanoes can erupt with a force thousands of times greater than ordinary volcanoes. While most volcanic eruptions are relatively modest events, a rare category of volcano is capable of eruptions so massive they can affect the entire planet. These are the supervolcanoes. A supervolcano is defined by its ability to erupt more than 1,000 cubic kilometers of material in a single event. For comparison, the 1880 Mount St. Helens eruption ejected about 1 cubic kilometer. A supervolcanic eruption would be over 1,000 times larger. The most famous supervolcano is the Yellowstone caldera in the United States. This massive volcanic system has produced 3 major eruptions over the past 2 million years. The largest of these, about 2.1 million years ago, ejected roughly 2,500 cubic kilometers of material. Supervolcanic eruptions are extremely rare, occurring perhaps once every several 100,000 years on average. But when they do occur, their effects can be global. They can inject so much ash and gas into the atmosphere that temperatures drop worldwide for years or even decades. The city of Pompeii was preserved beneath volcanic ash for nearly 2,000 years. On August 24th, in the year 79 of the Common Era, Mount Vesuvius erupted with devastating force. The Roman cities of Pompeii and Herculaneum, located near the base of the volcano, were buried under meters of volcanic ash and pyroclastic material. The burial happened so quickly that many aspects of daily life were preserved exactly as they had been at the moment of the eruption. Food sat on tables, graffiti remained on walls. Even the poses of victims were captured as the volcanic material hardened around them. When archaeologists began excavating Pompeii in the 18th century, they discovered a remarkably complete snapshot of Roman life. The city had been frozen in time, offering insights into ancient architecture, commerce, art, and daily routines that would otherwise have been lost to history. Today, Pompeii is one of the most important archaeological sites in the world. It teaches us not only about Roman civilization, but also about the power of volcanoes to both destroy and preserve. Magma becomes lava only when it reaches the surface. The terms magma and lava are often used interchangeably, but they actually refer to molten rock in different locations. Magma is the name for molten rock that remains beneath the Earth's surface. It collects in underground chambers, sometimes waiting for thousands or even millions of years before finding a pathway to the surface. While underground, magma may cool slowly, allowing large crystals to form, or it may remain hot and fluid, waiting for an eruption. When magma finally reaches the surface and emerges into the open air, it becomes lava. The transition is purely about location. The same molten rock that was magma deep underground is called lava once it flows across the landscape. This distinction helps scientists communicate more precisely about volcanic processes. The behavior of magma underground determines what kind of eruption will occur. The behavior of lava on the surface determines how it will affect the surrounding landscape. Pyroclastic flows are among the deadliest volcanic hazards. When we imagine volcanic danger, we often think of lava flows, but the most dangerous aspect of many eruptions is something far more terrifying: pyroclastic flows. A pyroclastic flow is a fast-moving cloud of superheated gas, ash, and rock fragments. These flows can race down the slopes of a volcano at speeds exceeding 100 kilometers per hour and sometimes much faster. The temperature inside a pyroclastic flow typically ranges from 200 to 700 degrees Celsius, hot enough to incinerate almost anything in its path. Unlike lava, which usually moves slowly enough to allow evacuation, pyroclastic flows give almost no warning and cannot be outrun. They were responsible for most of the deaths at Pompeii and Herculaneum. They killed nearly 30,000 people when Mount Pelée in Martinique erupted in 1902. For communities near explosive volcanoes, pyroclastic flows represents the greatest threat. Evacuation before an eruption begins is often the only protection. Some volcanic islands have appeared and disappeared within living memory. The ocean is a dynamic environment where new land can emerge from beneath the waves, only to be eroded away again within years or decades. In 1963, a volcanic eruption off the coast of Iceland created a new island called Surtsey. Over the following years, the island grew to about 2.5 square kilometers as additional eruptions added more material. Scientists have been studying Surtsey ever since, watching as life gradually colonizes the new land. Other volcanic islands have been less permanent. In 2015, an underwater eruption near Tonga created a new island that was initially expected to erode away quickly. Surprisingly, it has persisted longer than predicted, offering scientists an opportunity to study island formation and erosion in real time. The Hunga Tonga Hunga Hapai volcano in the same region produced a massive eruption in 2022, one of the largest in recent decades, which significantly altered the local geography. The birth and death of volcanic islands remind us that Earth's surface is never truly static. Lava tubes can extend for many kilometers underground. When a river of lava flows across the landscape, the surface may cool and harden while molten rock continues to flow beneath. If the lava eventually drains away, it can leave behind an empty tunnel called a lava tube. Some lava tubes are enormous. The Kazumura Cave in Hawaii extends for over 65 kilometers, making it one of the longest lava tubes ever discovered. Other notable lava tubes exist in Iceland, the Canary Islands, and many other volcanic regions. Inside a lava tube, the temperature remains relatively constant throughout the year. This makes them attractive for certain purposes. Some lava tubes have been used for storage, and scientists have proposed that similar structures on the Moon or Mars might provide natural shelter for future human habitats. Walking through a lava tube is like exploring the fossilized arteries of a volcano. The walls often show ripples and ledges that mark the levels at which lava once flowed. Volcanic ash can circle the globe. When a powerful eruption injects ash and gases high into the atmosphere, these materials can be carried around the world by high-altitude winds. The finest ash particles, along with sulfur dioxide and other volcanic gases, can reach the stratosphere, the layer of atmosphere between about 10 and 50 kilometers above the surface. Once there, they may remain suspended for months or even years. In 1883, the Krakatoa eruption put so much material into the stratosphere that sunsets around the world were unusually colorful for years afterward. The ash scattered sunlight in ways that created vivid red and orange skies. Some art historians have suggested that the distinctive skies in certain paintings from that era were influenced by volcanic aerosols. More recently, the 1991 eruption of Mount Pinatubo in the Philippines injected about 20 million tons of sulfur dioxide into the stratosphere. This created a global layer of sulfate particles that reflected enough sunlight to cool the planet by about 0.5 degrees Celsius for the following year. Volcanoes can affect climate far from their location. The climatic effects of major eruptions extend far beyond colorful sunsets. Volcanic aerosols in the stratosphere reflect incoming sunlight before it can warm the Earth's surface. This can cause measurable cooling that affects weather patterns around the world. The year without a summer following the Tambora eruption is the most famous example, but other eruptions have had similar effects on a smaller scale. The Pinatubo eruption caused temporary cooling that was detectable in global temperature records. Even moderate eruptions can influence regional weather patterns. Scientists study the relationship between volcanoes and climate to better understand how the Earth system works. Volcanic eruptions provide natural experiments that reveal how sensitive the climate is to changes in the amount of sunlight reaching the surface. Some researchers have even proposed that volcanic-style aerosol injection might be used deliberately to counteract global warming. This controversial idea, called stratospheric aerosol injection, remains speculative, but illustrates how volcanoes have shaped our understanding of climate. The Hawaiian Islands were created by a volcanic hotspot. The chain of Hawaiian Islands stretches across the Pacific Ocean in a line that extends for thousands of kilometers. This pattern is not random. It reflects the movement of the Pacific Plate over a stationary hotspot deep in the Earth's mantle. A hotspot is a plume of unusually hot material that rises from deep within the planet. As the tectonic plate moves over this hotspot, new volcanoes form on the surface above it. Over time, each volcano is carried away from the hotspot by plate motion, and a new volcano begins to form in its place. The result is a chain of islands arranged by age. The oldest Hawaiian islands, now eroded to small atolls and seamounts, are in the northwest. The youngest and most volcanically active islands are in the southeast, where they currently sit over the hotspot. A new volcanic mountain called Loihi is currently forming on the seafloor southeast of the Big Island. In tens of thousands of years, it will eventually emerge above the waves as the newest Hawaiian island. Calderas form when volcanoes collapse into emptied magma chambers. After a large eruption drains a significant amount of magma from an underground chamber, the overlying rock may lose its support. When this happens, the ground can collapse downward, creating a large depression called a caldera. Calderas can be many kilometers across and several hundred meters deep. They are among the most dramatic volcanic landforms on Earth. Some of the most famous examples include Crater Lake in Oregon, which formed about 7,700 years ago when Mount Mazama collapsed after a massive eruption. Other notable calderas include the Ngorongoro crater in Tanzania, now home to an extraordinary concentration of African wildlife, and the Yellowstone caldera, which encompasses much of Yellowstone National Park. The word caldera comes from the Spanish word for cauldron. When filled with water, these giant bowls can become strikingly beautiful lakes. Volcanoes exist on other planets and moons. Earth is not the only body in our solar system with volcanic activity. Volcanoes have been discovered on Venus, Mars, and several moons of the outer planets. Mars is home to the largest known volcano in the solar system. Olympus Mons rises about 22 kilometers above the surrounding plains and spans nearly 600 kilometers at its base. This enormous shield volcano is roughly 3 times the height of Mount Everest. It was able to grow so large because Mars lacks plate tectonics. The volcanic source remained stationary beneath the growing mountain, allowing material to accumulate in one place. Venus has more volcanoes than any other planet, with more than 1,600 major volcanic features identified on its surface. Scientists are still debating whether some of these volcanoes remain active today. Perhaps the most volcanically active body in the solar system is Io, one of Jupiter's moons. Io's surface is constantly being reshaped by hundreds of active volcanoes, some of which shoot plumes of sulfur compounds hundreds of kilometers into space. Cryovolcanism erupts ice instead of rock. In the outer solar system, where temperatures are far below freezing, a different kind of volcanism occurs. Instead of molten rock, these volcanoes erupt materials like water, ammonia, or methane that are frozen or slushy at the extreme cold of deep space. Scientists call these features cryovolcanoes, from the Greek word for cold. They have been identified on several moons and dwarf planets. Saturn's moon, Enceladus, is particularly famous for its cryovolcanic activity. Enormous geysers near the moon's south pole shoot plumes of water ice particles hundreds of kilometers into space. This material escapes to form one of Saturn's outer rings. The presence of liquid water beneath Enceladus's icy surface has made it a target of interest in the search for extraterrestrial life. Neptune's moon, Triton, also shows evidence of cryovolcanic activity. During the Voyager 2 flyby in 1989, dark plumes were observed rising from the moon's surface, possibly driven by nitrogen gas. Volcanic gases include water vapor, carbon dioxide, and sulfur dioxide. When a volcano erupts, it releases not only solid material, but also large quantities of gas. These volcanic gases play important roles in both the eruption process and the broader Earth system. Water vapor is typically the most abundant volcanic gas, often comprising more than 60% of emissions. Carbon dioxide, sulfur dioxide, hydrogen sulfide, and hydrogen chloride are also common. In smaller quantities, volcanoes release fluorine, helium, and various trace gases. The sulfur dioxide released during eruptions is responsible for many of the atmospheric effects we discussed earlier. When it reaches the stratosphere, it combines with water to form tiny droplets of sulfuric acid that scatter sunlight. Some volcanic gases are directly hazardous to life. Carbon dioxide is denser than air and can accumulate in low-lying areas, displacing oxygen. In 1986, a catastrophic release of carbon dioxide from Lake Nyos in Cameroon killed over 1,700 people in nearby villages. The gas had accumulated in the volcanic crater lake and was suddenly released, flowing downhill in an invisible, deadly wave. The Deccan Traps represent one of Earth's largest volcanic events. About 66 million years ago, at the same time as the dinosaur extinction, enormous volcanic eruptions occurred in what is now India. These eruptions continued for roughly 1 million years, releasing vast quantities of lava that covered an area of about 500,000 square kilometers. The resulting rock formations are called the Deccan Traps. The word trap comes from a Scandinavian word for stairs, describing the step-like appearance of the layered lava flows. Scientists debate the role these eruptions played in the dinosaur extinction. Some researchers believe the volcanic activity stressed global ecosystems and made them more vulnerable to the asteroid impact that occurred at the same time. Others think the Deccan eruptions alone could have caused the extinction. Most likely, both events contributed to the environmental catastrophe. The Deccan Traps remind us that volcanic activity can occur on scales far beyond anything in human experience. Similar massive eruptions, called flood basalt events, have occurred several times in Earth's history, often coinciding with major extinction events. Hydrothermal vents near underwater volcanoes support unique ecosystems. Deep on the ocean floor, where volcanic activity heats seawater, remarkable communities of life thrive in complete darkness. These hydrothermal vents release mineral-rich water at temperatures that can exceed 300 degrees Celsius. Around these vents, scientists have discovered ecosystems unlike any other on Earth. Giant tube worms, some over 2 meters long, cluster near the hot water. Blind shrimp, strange fish, and various crustaceans inhabit these deep-sea oases. Mats of specialized bacteria form the base of the food web. What makes these ecosystems remarkable is that they derive their energy not from sunlight, but from chemical reactions. The bacteria that form the foundation of vent communities use a process called chemosynthesis to extract energy from hydrogen sulfide and other chemicals in the vent water. The discovery of hydrothermal vent communities in the late 1970s revolutionized our understanding of where life can exist. It suggested that life might be possible in other extreme environments, including on moons like Europa and Enceladus that may have underwater volcanic activity. Volcanic mountains can grow surprisingly quickly. While most geological processes operate on timescales of millions of years, volcanic mountains can sometimes grow rapidly enough to observe. In 1943, a Mexican farmer named Dionisio Pulido witnessed the birth of a new volcano in his cornfield. Over the following week, a cone of ash and lava grew to over 50 meters tall. Within a year, the volcano named Paricutin had reached a height of over 300 meters by the time eruptions ceased in 1952. The cone stood 424 meters above the original field. Paricutin offered scientists an unprecedented opportunity to study a volcano throughout its entire life cycle, from birth to extinction. It also reminded the world that new volcanoes can appear almost anywhere in volcanically active regions. Other volcanoes have grown rapidly during periods of intense activity. Mount St. Helens rebuilt much of its dome within years of its 1980 eruption. The volcanic island of Surtsey emerged from the sea and grew to its maximum size within just a few years. Volcanic rock records Earth's magnetic field at the time of cooling. When lava cools and solidifies, iron-bearing minerals within the rock align with the Earth's magnetic field. Once the rock hardens, these minerals are locked in place, preserving a record of the magnetic field's direction and intensity at that moment. This phenomenon, called paleomagnetism, has been instrumental in understanding Earth's history. By studying the magnetization of volcanic rocks of different ages, scientists discovered that Earth's magnetic field periodically reverses, with the north and south magnetic poles switching places. These magnetic reversals occur at irregular intervals, sometimes separated by millions of years and sometimes by only tens of thousands of years. The record preserved in volcanic rocks allows scientists to date rocks and correlate geological events across different parts of the world. Paleomagnetism also provided crucial evidence for the theory of plate tectonics. The pattern of magnetic stripes on the ocean floor, recorded in volcanic rocks at mid-ocean ridges, demonstrated that new crust is constantly being created and spreading outward. Mount Fuji is considered one of the most beautiful volcanoes in the world. Rising to 3,776 meters, Mount Fuji is Japan's tallest peak and one of its most iconic landmarks. Its nearly perfect conical shape, often capped with snow, has inspired artists and poets for centuries. Mount Fuji is a stratovolcano built from alternating layers of lava and ash deposited during numerous eruptions over the past 100,000 years. The current symmetrical cone began forming about 10,000 years ago atop the remains of older volcanic structures. The volcano last erupted in 1707, producing ash that fell on the city of Edo, now Tokyo, about 100 kilometers away. While Mount Fuji is currently considered dormant rather than extinct, scientists continue to monitor it for signs of renewed activity. Each year, hundreds of thousands of people climb Mount Fuji during the summer season. From the summit, climbers can watch the sunrise over the Pacific Ocean, a site that has spiritual significance in Japanese culture. The mountain is designated as a UNESCO World Heritage Site, recognized for its cultural importance as well as its natural beauty. Volcanoes release enough heat to warm entire regions. The heat generated by volcanic activity can warm surrounding areas in ways that benefit human communities. This geothermal energy has been harnessed for various purposes throughout history. In Iceland, a country that sits atop a mid-ocean ridge, geothermal energy heats about 90% of homes. Hot water from volcanic sources is piped directly into buildings, providing warmth without burning fossil fuels. Geothermal power plants also generate a significant portion of Iceland's electricity. Similar geothermal resources are used in New Zealand, the Philippines, Indonesia, and parts of the United States. The city of Boise, Idaho, has been using geothermal heating since the 1890s. On a smaller scale, volcanic heat creates natural hot springs that have been valued for bathing and relaxation throughout human history. The Japanese onsen tradition, the Roman baths, and similar practices around the world all trace their origins to volcanic heat. Some volcanic craters contain acidic lakes. When a volcano's crater fills with water, the result can be a striking but hazardous lake. Many crater lakes are fed by volcanic gases that dissolve in the water, creating highly acidic conditions. Kawah Iyan in Indonesia contains one of the world's most acidic natural lakes. The water has a pH below 1, similar to battery acid. Despite these extreme conditions, the lake is a striking turquoise color due to dissolved minerals. Miners work near the lake, extracting sulfur deposits under dangerous conditions. Other crater lakes pose different hazards. As we mentioned, Lake Nyos in Cameroon accumulated deadly carbon dioxide that was suddenly released in 1986. A similar lake, called Lake Monone in the same region, released carbon dioxide 2 years earlier, killing 37 people. Not all crater lakes are dangerous. Crater Lake in Oregon is famous for its exceptional clarity and deep blue color. The lake formed in the caldera of Mount Mazama and is fed only by rain and snow, with no inlet or outlet streams. Its water is among the clearest in the world. Lava comes in different types with different properties. Not all lava behaves the same way. The chemical composition of molten rock determines how it flows, how explosive its eruptions can be, and what kind of landscape it creates. Basaltic lava, with its relatively low silica content, is typically thin and runny. It flows easily across the landscape, sometimes traveling many kilometers from the vent. This type of lava creates broad, gently sloped shield volcanoes like those in Hawaii. Andesitic and daxitic lavas have higher silica content and are more viscous. They flow less easily and often pile up near the vent, creating steeper volcanic cones. Eruptions involving these lavas tend to be more explosive because trapped gases cannot escape as easily from the thick magma. Rhyolitic lava with the highest silica content is extremely viscous. It barely flows at all, often forming lava domes that bulge upward near the vent. Rhyolitic eruptions can be violently explosive when accumulated pressure is suddenly released. The type of lava produced by a volcano determines much about its behavior and hazards. Volcanic eruptions can be predicted, but not with perfect accuracy. Scientists have made tremendous progress in monitoring volcanoes and predicting eruptions. Sensitive instruments detect the subtle warning signs that often precede volcanic activity. Seismometers record the small earthquakes caused by magma moving underground. GPS receivers measure tiny changes in the shape of a volcano as magma accumulates beneath the surface. Gas sensors detect changes in the composition and quantity of volcanic emissions. Satellites monitor surface temperature and deformation from space. These tools have allowed scientists to issue warnings before many eruptions, saving countless lives. The successful evacuation of areas around Mount Pinatubo before its 1991 eruption prevented what could have been a catastrophic death toll. However, prediction remains imperfect. Volcanoes do not always follow expected patterns. Some eruptions occur with little warning, while others are preceded by long periods of unrest that do not lead to eruptions. The 1985 disaster at Nevado del Ruiz in Colombia, where over 23,000 people died despite warnings from scientists, showed how difficult it can be to translate scientific predictions into effective evacuations. Shield volcanoes have gentle slopes built by fluid lava. Different types of volcanoes have distinctly different shapes, reflecting the nature of their eruptions. Shield volcanoes are broad mountains with gentle slopes, typically less than 10 degrees. They are built almost entirely from fluid basaltic lava that flows easily across the landscape. Each eruption adds a new layer to the volcano's flanks, gradually building the mountain over time. The name comes from their resemblance to a warrior's shield lying on the ground. Mauna Loa and the other Hawaiian volcanoes are classic examples of shield volcanoes. Similar structures exist on Mars, where the low gravity and lack of plate tectonics allowed them to grow even larger. Shield volcanoes rarely produce explosive eruptions. Instead, they typically feature lava fountains and flowing rivers of molten rock. While these eruptions can destroy property, they rarely cause loss of life because people have time to evacuate. Stratovolcanoes are steep cones prone to explosive eruptions. In contrast to shield volcanoes, stratovolcanoes are tall, steep-sided mountains with slopes that can exceed 30 degrees. They are built from alternating layers of lava, ash, and other volcanic materials, giving them their layered structure. Stratovolcanoes, also called composite volcanoes, are associated with the most dangerous types of eruptions. Their viscous magma traps gas until pressure builds to explosive levels. Many of history's most devastating eruptions have come from stratovolcanoes. Mount Vesuvius, Mount Fuji, Mount St. Helens, and Mount Pinatubo are all stratovolcanoes. They tend to form beautiful, symmetrical cones that become iconic features of their landscapes, but their beauty masks significant danger. The slopes of stratovolcanoes are often unstable. The same alternating layers that give them their structure also make them prone to landslides and lahars. Communities near stratovolcanoes must balance appreciation for their scenic beauty against awareness of their hazards. Lahars are volcanic mud flows that can travel great distances. When volcanic ash and debris mix with water, the result is a thick slurry that flows downhill with tremendous force. These volcanic mud flows, called lahars, are among the most far-reaching volcanic hazards. Lahars can be triggered by various mechanisms. Heavy rainfall on fresh ash deposits is a common cause. Eruptions that melt glaciers or crater lakes can release huge volumes of water that mix with volcanic material. Even years after an eruption, lahars can occur when rain mobilizes loose deposits. Once formed, lahars can travel for tens of kilometers, following river valleys and engulfing everything in their path. They move fast, sometimes exceeding 60 kilometers per hour, and give little warning. The consistency ranges from a slurry like wet concrete to a more watery flood. The 1985 lahar from Nevado del Ruiz traveled over 70 kilometers from the volcano, burying the town of Armero and killing most of its population. Mount Rainier in Washington state poses similar lahar hazards to communities in the surrounding valleys. Volcanic islands often become biodiversity hotspots. When new volcanic islands emerge from the ocean, they begin as barren rock, but over time, life finds a way to colonize these new lands, often evolving in remarkable directions. Volcanic islands are isolated laboratories of evolution. Seeds drift ashore on ocean currents. Birds arrive after long flights. Insects hitch rides on floating debris. With each new arrival, the ecological community becomes more complex. Because of their isolation, island species often evolve in unique ways. The Galapagos Islands, formed by volcanic activity, are famous for their unique wildlife. Darwin's observations there helped inspire his theory of evolution. The finches, tortoises, and iguanas of the Galapagos are found nowhere else on Earth. Similarly, the Hawaiian Islands support thousands of endemic species that evolved in isolation over millions of years. The silver sword plants, honey creeper birds, and happy-faced spiders of Hawaii represent remarkable evolutionary journeys that were made possible by volcanic isolation. Volcanoes have created some of Earth's most dramatic landscapes. From towering peaks to vast calderas, from black sand beaches to steaming geothermal fields, volcanoes have sculpted some of the most visually stunning landscapes on our planet. The towering peaks of the Cascade Range define the skyline of the Pacific Northwest. The geothermal wonderland of Yellowstone draws millions of visitors each year. The volcanic islands of the Mediterranean have inspired artists and writers for millennia. The dramatic landscapes of Iceland have become popular filming locations for movies and television. But volcanic landscapes are more than just scenery. They are records of Earth's dynamic processes written in stone. Each lava flow, each ash deposit, each hot spring tells a story of fire and transformation. When we visit volcanic landscapes, we are walking on the product of forces that operate on scales far beyond human experience. We are reminded that the ground beneath our feet is not permanent. It is part of a planet that is constantly changing. Let your breathing slow for a moment. We have traveled through many remarkable facts about volcanoes, from the depths of the ocean to the peaks of the highest volcanic mountains, from ancient eruptions that shaped human history to the quiet volcanic activity that continues today. Your body may be feeling heavier now, sinking deeper into rest. That is good. There is no need to hold on to any particular fact. Let them drift through your mind like volcanic ash settling slowly to the ground. We are not finished yet. There are still more wonders to explore, but there is no rush. The volcanoes will wait. Volcanic ash differs from the ash of ordinary fires. When we hear the word ash, we might think of the residue left after burning wood or paper, but volcanic ash is something quite different. Volcanic ash consists of tiny fragments of pulverized rock and volcanic glass. These particles are hard and abrasive, with sharp edges that can scratch surfaces and damage machinery. Unlike fire ash, which is soft and easily crumbles, volcanic ash can be surprisingly heavy when it accumulates. When volcanic ash falls on a building, it can add tremendous weight to the roof. Just a few centimeters of wet ash can cause roofs to collapse. Aircraft engines can be severely damaged if they fly through ash clouds, as the particles melt in the high temperatures of jet engines and coat internal components. The 2010 eruption of Eyjafjallajökull in Iceland disrupted air travel across Europe for weeks. Airlines canceled over 100,000 flights to avoid the volcanic ash cloud, affecting millions of passengers. It was a vivid reminder of how volcanic activity in one location can have far-reaching effects. Volcanoes have been worshipped as gods throughout human history. Across cultures and continents, humans have attributed divine significance to volcanoes. Their power, unpredictability, and otherworldly appearance made them natural objects of reverence and fear. The Hawaiian goddess Pele was believed to live in the crater of Kilauea. Offerings were made to appease her and avoid her fiery wrath. To this day, some visitors to Hawaii leave offerings at volcanic sites. The people of Java in Indonesia have long performed ceremonies at the crater of Mount Bromo, throwing offerings into the volcanic vent to ensure good harvests and protection from eruptions. Similar practices exist at volcanoes around the world. These religious traditions reflect a deep human understanding that volcanic forces are beyond our control. We can study volcanoes, monitor them, and sometimes predict their eruptions, but we cannot stop them. In the face of such power, reverence seems a natural response. The explosive energy of some eruptions rivals nuclear weapons. When we try to comprehend the power of volcanic eruptions, comparisons to more familiar energy releases can help. The 1980 eruption of Mount St. Helens released energy equivalent to about 24 megatons of TNT. This is roughly 1,600 times the energy of the atomic bomb dropped on Hiroshima. The 1883 Krakatoa eruption was even more powerful, releasing energy equivalent to about 200 megatons of TNT. This is 4 times the largest nuclear weapon ever detonated. And supervolcanic eruptions dwarf even these figures. The Yellowstone eruption, 2.1 million years ago, may have released energy equivalent to tens of thousands of megatons. These numbers are almost meaningless in their magnitude, but they help illustrate why volcanic eruptions can have effects that extend around the globe and why they have shaped Earth's history in profound ways. Volcanic rock is used in construction around the world. Humans have long made practical use of the materials produced by volcanoes. The durability and availability of volcanic rock have made it a common construction material throughout history. Tuff, a rock formed from consolidated volcanic ash, is relatively soft and easy to carve. Ancient peoples used it to create everything from buildings to statues. The famous moai of Easter Island were carved from volcanic tuff. The rock-cut churches of Cappadocia in Turkey were hollowed from volcanic deposits. Basalt, the most common volcanic rock, is extremely durable and has been used for paving, construction, and breakwaters. The ancient Romans used basalt for paving their famous roads. In modern times, volcanic materials find many uses. Pumice is used as an abrasive in products ranging from soap to industrial polishing compounds. Volcanic cinder is used in landscaping. Basalt fibers are used as reinforcement in composite materials. The products of volcanic eruptions continue to serve human needs. Some eruptions create their own weather systems. Large volcanic eruptions can affect local weather in dramatic ways. The enormous heat released during an eruption creates powerful updrafts that can reach far into the atmosphere. These updrafts can trigger the formation of cumulonimbus clouds, the same type of clouds that produce thunderstorms. Heavy rainfall often accompanies volcanic eruptions, as water vapor released from the magma and drawn up from the surrounding air condenses in the rising plume. The rainfall can be a mixed blessing. While it helps to clear ash from the air, it can also trigger lahars by mobilizing loose volcanic material on the slopes. The combination of rain and ash can produce muddy floods that travel far from the volcano. In some cases, volcanic eruptions have even produced snow. When the rising plume reaches high enough altitudes, the moisture it carries can freeze and fall back to the surface as precipitation. Volcanic activity helped create Earth's atmosphere. In the earliest days of our planet, there was no atmosphere as we know it today. The air we breathe is largely the product of billions of years of volcanic outgassing. Volcanoes release gases from the Earth's interior, including water vapor, carbon dioxide, nitrogen, and various other compounds. Over geological time, these volcanic emissions accumulated to form the oceans and atmosphere. The water vapor released by ancient volcanoes eventually condensed to form the first oceans. The nitrogen released became the dominant component of our atmosphere. The carbon dioxide played a role in regulating early climate. In this sense, we owe our very existence to volcanic activity. Without volcanoes, there would be no air to breathe, no oceans to moderate our climate, and likely no life as we know it. The same forces that can cause devastating eruptions have also made our planet habitable. Volcanic eruptions can turn day into night. When a sufficiently powerful eruption ejects enough material into the atmosphere, it can block out the sun entirely, plunging nearby areas into artificial darkness. Accounts from historical eruptions describe this terrifying phenomenon. During the Krakatoa eruption in 1883, darkness fell across a wide area. People in towns dozens of kilometers away needed lanterns at midday as the ash cloud blocked all sunlight. Similar darkness was reported during the Tambora eruption in 1815. Witnesses described the sky becoming so dark that they could not see their hands in front of their faces. The psychological impact was profound, with some people believing that the end of the world had come. Even when the ash cloud is not thick enough to create total darkness, eruptions can produce eerie twilight conditions. The sky takes on strange colors as sunlight is scattered by volcanic particles. Days seem dim, and sunsets glow with unusual intensity. Volcanic domes can grow and collapse repeatedly. After some volcanic eruptions, thick lava accumulates near the vent and piles up into a mound called a lava dome. These structures can grow slowly over weeks or months, swelling upward like bread rising in an oven. But lava domes are inherently unstable. Gas and pressure continue to build within them. The outer surface cools and hardens, while the interior remains hot and plastic. Eventually, part of the dome may collapse. When a lava dome collapses, it can trigger pyroclastic flows. The sudden release of pressure allows hot gas and rock to explode outward and race down the volcano slopes. Some of the deadliest volcanic events in history have been caused by dome collapses. Mount St. Helens has rebuilt its lava dome multiple times since the 1980 eruption. Each episode of dome growth is monitored carefully for signs of instability. The volcano remains a natural laboratory for understanding these dangerous but fascinating structures. Volcanic tremor signals magma movement underground. Scientists monitoring volcanoes pay close attention to a particular type of seismic signal called volcanic tremor. Unlike ordinary earthquakes, which produce sharp, discrete signals, volcanic tremor is a continuous vibration that can last for hours or days. Tremor is produced by the movement of magma or volcanic fluids through underground channels. The character of the tremor, including its frequency and intensity, can provide information about what is happening beneath the surface. Changes in volcanic tremor often precede eruptions. An increase in tremor intensity may indicate that magma is rising toward the surface. Changes in tremor frequency may signal that conditions in the underground plumbing system are changing. By monitoring tremor and other seismic signals, scientists can often detect volcanic unrest weeks or months before an eruption occurs. This early warning capability has saved many lives. The viscosity of magma determines eruption style. One of the most important factors in determining how a volcano will erupt is the viscosity of its magma, which is essentially how thick and sticky the molten rock is. Low viscosity magmas, like basalt, flow easily. Gases can escape from them without building up dangerous pressure. Eruptions of low viscosity magma tend to be relatively gentle, producing lava flows rather than explosions. High viscosity magmas like rhyolite and dacite resist flowing. Gases become trapped within them, unable to escape until the pressure builds to explosive levels. When these magmas finally erupt, they often do so violently. Viscosity is primarily controlled by the silica content of the magma. Silica molecules link together in chains that make the magma more resistant to flow. Understanding the relationship between magma composition and eruption style helps scientists assess volcanic hazards. Volcanic winters have occurred multiple times in history. When major eruptions inject sulfur dioxide into the stratosphere, the resulting sulfate aerosols can cause significant cooling that affects climate around the world. These episodes of volcanic cooling have occurred many times in Earth's history. The year without a summer in 1816, following the Tambora eruption, is the best documented volcanic winter, but similar events have occurred before and since. The eruption of Huayna in Peru in 1600 caused widespread cooling and crop failures in Russia and other parts of the northern hemisphere. The Laki eruption in Iceland in 1783 caused severe weather across Europe. The Pinatubo eruption in 1991 caused measurable cooling in the following years. Some scientists believe that even larger volcanic events in the distant past may have caused more severe climatic effects. The Toba eruption about 74,000 years ago has been suggested as a cause of a prolonged cold period that may have reduced human populations to small numbers. Geothermal energy from volcanoes is renewable and sustainable. The heat generated by volcanic activity represents a vast energy resource. Unlike fossil fuels, which are finite and produce greenhouse gases, geothermal energy is renewable and produces minimal emissions. Geothermal power plants tap into reservoirs of hot water and steam beneath the Earth's surface. This heat is ultimately derived from the same sources that power volcanoes: the decay of radioactive elements deep in the Earth and the residual heat from the planet's formation. Countries with significant volcanic activity have been leaders in developing geothermal energy. Iceland generates roughly a quarter of its electricity from geothermal sources. The Philippines, Indonesia, and Kenya also have significant geothermal capacity. As the world seeks to transition away from fossil fuels, volcanic regions offer a natural advantage. The same geological forces that create hazards also provide opportunities for clean, sustainable energy production. Scientists who study volcanoes are called volcanologists. The scientific study of volcanoes is called volcanology, and those who dedicate their careers to this work are volcanologists. These scientists combine knowledge from geology, physics, chemistry, and many other fields to understand volcanic processes. Volcanologists work in some of the most challenging environments on Earth. They climb active volcanoes to collect samples and install monitoring equipment. They measure gas emissions from steaming vents. They analyze rocks to reconstruct the history of past eruptions. The work can be dangerous. Several volcanologists have lost their lives while studying active volcanoes, caught by unexpected eruptions or overcome by toxic gases. But their courage has saved countless others by advancing our understanding of volcanic hazards and improving prediction. Modern volcanologists use sophisticated tools, including satellite remote sensing, computer modeling, and advanced chemical analysis. But fieldwork on active volcanoes remains essential. There is no substitute for direct observation of these remarkable natural laboratories. Volcanic rocks tell stories of ancient eruptions. Every volcanic rock contains information about the conditions under which it formed. By studying these rocks, scientists can reconstruct eruptions that occurred millions or even billions of years ago. The texture of a volcanic rock reveals how quickly it cooled. Fine-grained rocks cooled rapidly, while rocks with larger crystals cooled more slowly. The presence of gas bubbles, called vesicles, indicates that the magma contained dissolved gases that escaped as the rock solidified. The chemical composition of volcanic rocks provides information about the magma's origin deep in the earth. Different rock types form from different types of magma, and careful analysis can trace the rock's history from deep mantle sources to surface eruptions. By reading these rocky stories, scientists have reconstructed Earth's volcanic history going back billions of years. Ancient volcanic rocks provide evidence of conditions on the early Earth, including the composition of the atmosphere and the temperature of the oceans. Volcanic plugs are towers of rock that mark ancient eruptions. When a volcano becomes extinct and erosion wears away the softer surrounding material, sometimes only the hardened magma that once filled the volcanic conduit remains. These resistant cores, called volcanic plugs or necks, can stand as dramatic towers rising from the landscape. Devil's Tower in Wyoming is perhaps the most famous volcanic plug in the United States. This striking monument rises nearly 300 meters above the surrounding terrain. Its distinctive columnar shape was formed as the magma cooled and contracted, creating the vertical columns that make it so recognizable. Shiprock in New Mexico is another dramatic example. This jagged peak rises nearly 500 meters above the desert floor and is sacred to the Navajo people. The radiating dikes that extend from it mark channels where magma once flowed outward from the central conduit. Volcanic plugs can take millions of years to be exposed by erosion. They reveal the hidden plumbing systems of ancient volcanoes that have long since disappeared. Pumice is the only rock that floats on water. When gas-rich magma erupts violently, the rapid expansion of gas bubbles can create a rock so full of empty spaces that it's lighter than water. This rock is called pumice. Pumice forms when lava froths with escaping gases and then cools so quickly that the bubbles are preserved as tiny cavities throughout the rock. The resulting material can be more than 50% empty space. After major eruptions, rafts of floating pumice can cover vast areas of the ocean's surface. These rafts drift with currents and winds, sometimes traveling thousands of kilometers before eventually washing up on distant shores. Scientists have tracked pumice rafts from eruptions in the South Pacific all the way to Australia. Pumice rafts carry marine organisms between islands, potentially contributing to the spread of species across the oceans. They are also used commercially as an abrasive in products ranging from soap to industrial polishing compounds. Some volcanoes produce diamonds. Deep within the Earth, under conditions of extreme pressure and temperature, carbon atoms can crystallize into diamonds. Occasionally, volcanic eruptions bring these precious stones to the surface. The type of eruption that carries diamonds is extremely rare and violent. These eruptions originate from depths of 150 kilometers or more, far deeper than most volcanic activity. The magma rises so rapidly that the diamonds do not have time to convert to graphite, their more stable form at the surface. The volcanic pipes that carry diamonds to the surface are called kimberlite pipes, named after the town of Kimberley in South Africa, where they were first studied. Most of the world's diamonds come from these ancient volcanic structures. Interestingly, no kimberlite eruption has occurred in recorded human history. All known diamond-bearing pipes are ancient, dating back millions or even billions of years. We can only imagine the violence of these eruptions based on the geological evidence they left behind. Volcanic earthquakes often precede eruptions. Before magma reaches the surface, it must push its way through solid rock. This movement generates earthquakes that seismometers can detect. Volcanic earthquakes differ from tectonic earthquakes in several ways. They tend to be shallower, occurring within a few kilometers of the surface. They often cluster in swarms, with many small earthquakes occurring close together in time, and their pattern often changes in characteristic ways as magma approaches the surface. By monitoring volcanic earthquakes, scientists can often detect unrest weeks or months before an eruption occurs. An increase in earthquake frequency or a change in their depth may signal that magma is on the move. The relationship between earthquakes and eruptions is not perfect. Some earthquake swarms do not lead to eruptions, and some eruptions occur with relatively little seismic warning. But earthquake monitoring remains one of the most important tools in the volcanologist's toolkit. Volcanic glass can be sharper than surgical steel. We mentioned earlier that obsidian was used for cutting tools throughout human history, but the sharpness of volcanic glass is more than a historical curiosity. When obsidian fractures, it can produce edges that are only a few molecules thick. This is far sharper than even the finest steel blades, which have edges that are relatively rough at the molecular level. Some modern surgeons have experimented with obsidian scalpels for delicate procedures. The extremely sharp edge can cut tissue with less damage than metal blades, potentially reducing scarring and improving healing. However, obsidian is brittle and can break during surgery, so its use remains limited. For ancient peoples, obsidian was as valuable as metal would later become. Trade networks spanning thousands of kilometers developed to distribute obsidian from volcanic sources to distant communities. Archaeologists can trace the chemical signatures of different obsidian sources, revealing ancient trade routes. Mount Tambora's eruption was the largest in recorded history. We have mentioned the effects of the Tambora eruption several times, but the scale of the event deserves fuller description. In April 1815, Mount Tambora in Indonesia exploded with a force that dwarfed any eruption in centuries. The mountain had stood over 4,000 meters tall. After the eruption, its summit was gone, replaced by a caldera over 6 kilometers wide. The eruption ejected approximately 160 cubic kilometers of material into the atmosphere. This is roughly 100 times more than the 1980 St. Helens eruption. The explosion was heard over 2,000 kilometers away. At least 70,000 people died from the direct effects of the eruption, making it one of the deadliest in history. But the indirect effects were even far-reaching. The volcanic aerosol that spread around the globe caused the year without a summer in 1816, with crop failures and famine affecting millions. Tambora remains a reminder of what volcanoes are capable of at their most extreme. Some volcanic craters are home to rare ecosystems. The unique conditions found in volcanic craters can support species found nowhere else on Earth. The isolation, unusual chemistry, and stable microclimates of these environments create opportunities for evolution. Lake Nyos in Cameroon, despite its deadly carbon dioxide releases, supports fish adapted to the lake's unusual chemistry. Crater lakes in other parts of the world host endemic species of fish, invertebrates, and plants that evolved in isolation. Some volcanic craters maintain nearly constant temperatures year-round due to geothermal heating. These warm refugia can support tropical species, even in otherwise temperate climates. Researchers have found unexpected diversity in crater environments that were once assumed to be too harsh for life. The volcanic islands we discussed earlier are well known for their unique species, but even individual craters can function as evolutionary islands, separated from surrounding ecosystems by steep walls and harsh conditions. Volcanic ash layers serve as time markers in geology. When major eruptions deposit ash over wide areas, they create distinct layers that can be recognized across different locations. These ash layers serve as invaluable time markers for geologists and archaeologists. The study of volcanic ash layers is called tephrochronology. By analyzing the chemical composition of ash, scientists can often identify which volcano produced it, and sometimes even which specific eruption. This allows them to correlate events in different locations. For example, the eruption of Mount Mazama that created Crater Lake about 7,700 years ago deposited ash across much of the Pacific Northwest. Wherever archaeologists find this distinctive ash layer, they know they have reached that moment in time. Volcanic ash layers have helped date archaeological sites, trace ancient climate changes, and understand the frequency of eruptions over geological time. They are natural timestamps written into the Earth's layers. Some volcanoes glow at night with an eerie light. Active volcanoes with exposed lava or hot vents can produce a distinctive glow that is visible for kilometers at night. This volcanic glow has fascinated observers throughout history. The glow comes from incandescent lava or from hot gases and steam illuminated from below. Different volcanic materials glow at different colors depending on their temperature. The hottest lavas glow bright yellow-white, while cooler material glows orange or red. Some volcanoes, like Stromboli in Italy, have been providing nighttime illumination for millennia. Ancient sailors used these glowing summits as navigational aids. The steady rhythm of light from Stromboli's regular explosions earned it the nickname we mentioned, the Lighthouse of the Mediterranean. In Hawaii, the glow from active lava flows can light up clouds from below, creating dramatic red and orange skies. This volcanic haze, called VOG when mixed with fog, is both beautiful and potentially hazardous. Volcanic islands can sink back beneath the waves. The same forces that create volcanic islands eventually cause them to disappear. Over millions of years, volcanic islands undergo a predictable life cycle. When a new volcano forms, it rises above the sea surface and begins to grow. Fresh eruptions add material, building the island higher. But once volcanic activity ceases, the island's fate is sealed. The oceanic crust carrying the island slowly cools as it moves away from mid-ocean ridges or hotspots. As it cools, it becomes denser and sinks. At the same time, erosion wears down the island from above. Eventually, it slips below sea level. First, it becomes an atoll, a ring of coral surrounding a central lagoon where the island once stood. Finally, it becomes a seamount, a submerged mountain peak far beneath the waves. The Emperor Seamount chain in the Pacific consists of former Hawaiian islands that have undergone this transformation over tens of millions of years. Volcanic eruptions can produce valuable mineral deposits. The heat and chemicals associated with volcanic activity can concentrate valuable metals into mineable deposits. Many of the world's most important mines are located in volcanic regions. Hydrothermal systems associated with volcanoes circulate hot, mineral-rich fluids through the crust. As these fluids cool, they deposit metals like gold, silver, copper, and zinc in veins and other structures. The result can be ore deposits of considerable economic value. The volcanic island arc of Indonesia is rich in such deposits. The mountains of Chile and Peru, built by volcanic activity along the Andes, contain some of the world's largest copper mines. The gold deposits of the Philippines are associated with volcanic rocks. The same volcanic forces that create natural hazards also create the mineral wealth that has shaped human economies throughout history. The study of volcanoes has advanced our understanding of Earth as a system. Volcanology has contributed to many branches of science beyond the study of eruptions themselves. Volcanoes are windows into the Earth's interior and key components of the global systems that sustain life. The study of volcanic rocks led to discoveries about the composition of Earth's mantle and the processes that generate magma at depth. Volcanic gases provided clues about the early atmosphere and the origins of the oceans. The relationship between volcanic eruptions and climate has taught us about the sensitivity of Earth's climate system. The discovery of life at hydrothermal vents expanded our understanding of where life can exist. Modern volcanology is deeply connected to studies of plate tectonics, climate science, ecology, and even astrobiology. The questions volcanologists ask lead to insights that reach far beyond any single volcano. Volcanic landscapes inspire artists, writers, and dreamers. Throughout human history, volcanoes have captured the imagination. Their dramatic forms and powerful eruptions have inspired countless works of art, literature, and music. The Roman writer Pliny the Younger gave us one of the earliest detailed descriptions of a volcanic eruption in his account of Vesuvius in 79 CE. His letters describing the death of his uncle Pliny the Elder during that eruption remain valuable historical documents. Artists have been drawn to volcanic subjects for centuries. The paintings of Joseph Wright of Derby captured the drama of Vesuvius in eruption. The Japanese artist Hokusai created his famous series of views of Mount Fuji. Contemporary photographers continue to document the beauty and power of volcanic landscapes. Even in fiction, volcanoes appear as settings for drama and adventure. From Jules Verne's Journey to the Center of the Earth to modern films featuring volcanic disasters, these mountains of fire continue to ignite human imagination. Volcanic soils support some of the world's finest coffee. The relationship between volcanoes and agriculture extends to specialty crops prized for their quality. Coffee grown on volcanic slopes is particularly valued. The volcanic soils of regions like Central America, Ethiopia, and Indonesia provide ideal conditions for coffee plants. The well-drained, mineral-rich soils produce beans with complex flavors that command premium prices. The slopes of volcanoes also offer the altitude and temperature conditions that coffee prefers. Many of the world's most celebrated coffee-growing regions are found on active or dormant volcanic peaks. This is another example of how communities balance the risks and benefits of living near volcanoes. The same forces that can threaten their lives also provide the exceptional growing conditions that support their livelihoods. The largest recorded earthquake was associated with volcanic activity. In 1960, a massive earthquake struck Chile with a magnitude of 9.5, the largest ever recorded by modern instruments. This earthquake was associated with the tectonics of the Andes, where volcanic activity is driven by subduction. The earthquake triggered tsunamis that crossed the Pacific, causing casualties as far away as Hawaii and Japan. It also triggered volcanic eruptions and landslides throughout the affected region. While not directly caused by volcanic processes, this earthquake illustrates the connection between volcanic regions and seismic activity. The same plate boundaries that create volcanoes also generate earthquakes. The energy released by this single earthquake was equivalent to about 22% of all earthquake energy released during the entire 20th century. It was a reminder of the immense forces at work in our planet's most active zones. Some volcanic gases are used in industry. The gases released by volcanoes include compounds that have important industrial applications. By understanding volcanic gas chemistry, scientists have developed methods to harness these resources. Sulfur from volcanic sources has been collected and used by humans for thousands of years. The miners of Kawah Ijen in Indonesia continue a tradition of extracting pure sulfur from volcanic vents. Sulfur is used in fertilizers, chemicals, and many industrial processes. Carbon dioxide from volcanic sources is captured and used in various applications. Helium, a valuable industrial gas, is sometimes found associated with volcanic systems. Even the heat from volcanic gases can be harnessed directly. Volcanic resources extend beyond the obvious lava and ash. The invisible gases that escape from vents represent another way that humans have learned to benefit from volcanic activity. And now let us pause once more. You have journeyed with me through many more facts about the world of volcanoes. Your breathing may have slowed. Your body may feel heavy and comfortable. That is exactly as it should be. The stories of fire and stone, of ancient eruptions and quiet hot springs have carried you closer to rest. There is no need to remember any particular fact. Let them settle like volcanic ash, becoming part of the landscape of your dreams. We have only a little way left to travel, and then sleep. The future of volcanology holds many discoveries. Despite all we have learned, many mysteries about volcanoes remain. Future research will answer questions we have not yet thought to ask. New technologies are transforming how we study volcanoes. Drones can fly into ash plumes and over active lava flows, collecting data too dangerous for humans to obtain. Satellites monitor volcanic activity around the world, detecting changes that might otherwise go unnoticed. Machine learning and artificial intelligence are being applied to volcanic monitoring data, potentially revealing patterns that humans cannot see. Improved computer models simulate eruptions with increasing accuracy, helping communities prepare for disasters. The next generation of volcanologists will inherit both our knowledge and our questions. They will develop new tools, propose new theories, and make discoveries that we cannot imagine today. The study of volcanoes is far from complete. Every volcanic eruption is unique. No two eruptions are exactly alike. Even the same volcano can behave differently from one eruption to the next. The chemistry of the magma may change over time. The plumbing system beneath the volcano may reorganize itself between eruptions. Weather conditions, the presence of water, and countless other factors affect how an eruption unfolds. This variability makes prediction challenging. Just because a volcano behaved a certain way in the past does not guarantee it will behave the same way in the future. Each eruption must be approached with fresh observations and careful analysis. For scientists, this unpredictability is part of what makes volcanoes so fascinating. For communities living near volcanoes, it is a reminder to remain vigilant. The next eruption might be exactly like the last, or it might be completely different. Volcanoes connect us to the deep time of Earth's history. When we contemplate volcanoes, we're thinking about processes that operate on timescales far beyond human experience. The mountains we see today are the products of activities spanning millions of years. Some volcanic features preserve evidence of events billions of years old. This perspective can be both humbling and comforting. Our individual lives are brief flickers in geological time. The concerns that feel so urgent today will be forgotten long before the next major volcanic event reshapes the landscape. And yet, we are part of this vast story. The atoms in our bodies were forged in stellar explosions, processed through Earth's volcanic systems, and assembled by life into the forms we now inhabit. We are temporary arrangements of matter that will eventually return to the cycles of rock and fire. There is something peaceful in accepting our place in deep time. We need not solve every problem or answer every question. The Earth will continue its slow transformation whether we worry about it or not. The connection between humans and volcanoes will endure. As long as humans live on this planet, we will live with volcanoes. They are too numerous to avoid and too useful to abandon entirely. Future generations will develop new technologies for monitoring and perhaps even influencing volcanic activity. They will build communities that are better prepared for eruptions. They will continue to harness geothermal energy and benefit from volcanic soils. But they will also face the same fundamental reality that we face today. Volcanoes are beyond our control. We can study them, monitor them, and sometimes predict them, but we cannot stop them. We must learn to live with them. This relationship with the powerful and unpredictable forces of nature is part of what it means to be human on Earth. Volcanoes remind us of our place in a world that is far older and far more powerful than ourselves. Volcanic mountains often have distinctive vegetation zones. As you climb the slopes of a volcanic mountain, you pass through distinct ecological zones. The warm, moist base may support tropical forests. Higher up, the vegetation transitions to montane forest, then to alpine meadows, and finally to bare rock and ice near the summit. This zonation is compressed on volcanic slopes compared to ordinary mountains. Volcanoes often rise steeply from low elevations to great heights, packing many climate zones into a short horizontal distance. Each zone supports different species of plants and animals, creating remarkable biodiversity on a single mountain. The fertile volcanic soils enhance this diversity. Plants that might struggle elsewhere thrive on the mineral-rich slopes. In turn, these plants support insects, birds, and other animals in complex food webs. Some volcanic islands, like the Galapagos and Hawaii, are famous for their unique ecosystems. But even individual volcanoes on continents can function as ecological islands, harboring species adapted to their specific conditions. The chemistry of volcanic rocks reveals Earth's internal processes. Geochemists study the chemical composition of volcanic rocks to understand what happens deep within our planet. Each rock is a message from the Earth's interior, carrying information about conditions far beneath the surface. Different elements behave differently as magma forms and rises. Some elements concentrate in the liquid melt, while others remain behind in solid rocks. By measuring these chemical patterns, scientists can infer the depth at which magma formed, the temperature of its source, and the processes that modified it during its journey to the surface. Isotope ratios provide additional clues. Different isotopes of elements like strontium, neodymium, and lead have characteristic signatures that can identify the sources of volcanic material. These isotopic fingerprints have revealed that some volcanic rocks come from material that has been recycled through the mantle over billions of years. The chemical study of volcanic rocks has transformed our understanding of how our planet works at its deepest levels. Some cultures have developed sophisticated traditions for living near volcanoes. Communities that have lived near active volcanoes for generations have developed cultural practices that help them coexist with these powerful neighbors. In Japan, the tradition of volcanic hot springs or onsen is central to the culture of bathing and relaxation. Japanese communities have learned to harness volcanic heat while respecting the dangers it represents. Rituals and festivals honor local volcanoes as sacred places. In Indonesia, where millions of people live near active volcanoes, traditional knowledge about eruption signs has been passed down through generations. This knowledge complements modern scientific monitoring, helping communities respond to volcanic threats. The Maori people of New Zealand incorporated geothermal areas into their way of life, using hot springs for cooking, bathing, and heating. Their traditional knowledge about these volcanic landscapes is now recognized as an important complement to scientific understanding. Volcanic sunsets can be visible around the world. We mentioned earlier that volcanic aerosols can create colorful sunsets, but the beauty of these sunsets deserves more attention. When sulfur dioxide and fine ash particles reach the stratosphere, they scatter sunlight in distinctive ways. Sunsets and rises can take on vivid shades of red, orange, pink, and purple that persist for months or even years after a major eruption. After the Krakatoa eruption in 1883, sunsets around the world were so spectacular that they were noted in newspapers and diaries across multiple continents. Some art historians believe that the unusual skies depicted in Edvard Munch's painting The Scream may have been influenced by these volcanic sunsets. The 1815 Tambora eruption produced similarly dramatic effects. The painter J.M.W. Turner created works during this period that featured unusually vivid sunset colors, which some scholars attribute to volcanic aerosols. Nature and art intersect in the skies colored by volcanic fire. The heat flow from volcanoes reveals Earth's internal temperature. Scientists measure the heat escaping from volcanic regions to understand the thermal structure of our planet. This heat flow provides information about temperatures and processes deep underground. Near active volcanoes, heat flow can be many times higher than the global average. This excess heat represents thermal energy rising from magma bodies and hot rocks at depth. By mapping heat flow patterns, scientists can locate magma chambers and predict where volcanic activity is likely to occur. Heat flow measurements have practical applications as well. They help identify locations suitable for geothermal power development. They inform models used to predict volcanic behavior. They contribute to our understanding of how heat moves through the Earth's crust. The warmth of volcanic regions is not just a sensation we can feel at hot springs. It is a measurable phenomenon that tells us about the hidden fire beneath our feet. Volcanic eruptions have inspired numerous works of fiction. Beyond the art and poetry we mentioned, volcanoes have featured prominently in novels, films, and other fictional works. Their drama and danger make them natural settings for adventure stories. Jules Verne's Journey to the Center of the Earth climaxes with the protagonist escaping through a volcanic eruption. The destruction of Pompeii has been depicted in countless novels and films. Disaster movies regularly feature volcanic threats, from the lava flows of Dante's Peak to the supervolcanic eruption portrayed in Supervolcano. Science fiction has imagined volcanic worlds beyond Earth, often with remarkable accuracy. Long before spacecraft confirmed the volcanic nature of Io, writers speculated about volcanic moons and planets in our solar system. These fictional portrayals shape public perception of volcanoes. They can exaggerate dangers for dramatic effect, but they also inspire interest in the real science of volcanology. The minerals in volcanic rocks have many practical uses. Beyond the construction materials we discussed, volcanic rocks contain minerals with diverse applications in modern life. Zeolites, minerals that form in volcanic environments, are used as molecular sieves in water purification, as catalysts in chemical processes, and as additives in animal feed. Their unique crystal structures create tiny channels that can trap specific molecules. Bentonite, a clay mineral derived from volcanic ash, is used in drilling fluids, as a sealant for ponds and landfills, and even in cosmetics and medicines. Its ability to absorb water and swell makes it useful in many applications. Pearlite, volcanic glass that expands when heated, is used as lightweight aggregate in construction, as a soil amendment in gardening, and as an insulating material. It is the expanded form of a rock that originated as volcanic lava. The volcanic origin of these materials often goes unnoticed, but volcanic products surround us in everyday life. Remote sensing has revolutionized volcano monitoring. Before satellites, monitoring volcanoes required scientists to be physically present, often in dangerous locations. Today, remote sensing allows us to watch volcanoes from space. Satellites can detect thermal changes indicating rising magma. They can measure tiny ground movements that signal inflation or deflation of volcanic systems. They can track ash clouds as they spread through the atmosphere. Infrared sensors reveal heat patterns invisible to the naked eye. Radar instruments can see through clouds and darkness. Multiple satellite systems provide continuous coverage of volcanic regions around the world. This technology has saved lives. When Mount Pinatubo showed signs of unrest in 1991, satellite data helped scientists assess the threat and authorities order evacuations. Similar surveillance continues today at volcanoes across the globe. Remote sensing has made the entire planet a laboratory for volcanologists. The pace of volcanic activity varies widely. Some volcanoes erupt almost constantly, while others sleep for centuries between eruptions. Understanding this variability is essential for assessing volcanic hazards. Kilauea in Hawaii erupted almost continuously for 35 years before pausing in 2018. Stromboli has been erupting for over 2,000 years. These persistently active volcanoes allow scientists to study volcanic processes in real time. Other volcanoes have much longer repose periods. Mount Pinatubo was silent for over 100 years before its 1991 eruption. Mount St. Helens was silent for over a century before awakening in 1980. These long dormant periods can lull communities into complacency. The most dangerous situation may be a volcano that has been quiet so long that people forget it is there. When such a volcano finally awakens, communities may be unprepared for the consequences. Volcanic landscapes can recover remarkably quickly. After an eruption devastates a landscape, life begins to return sooner than we might expect. The recovery process reveals nature's resilience. In the blast zone around Mount St. Helens, life returned within years of the 1980 eruption. Seeds blew in from surrounding areas. Burrowing animals that survived underground emerged to find a new landscape. Plants sprouted from roots that had been protected beneath the ash. Today, the Mount St. Helens blast zone supports a diverse ecosystem. The recovery is not complete, and the area looks very different from what existed before, but life has adapted to the new conditions. Similar recovery has been documented at volcanoes around the world. Each eruption creates not just destruction, but also opportunity. The bare ground left behind is a canvas for ecological succession, the process by which simple communities give way to more complex ones over time. And now, truly, we approach the end. You have journeyed with me through the world of volcanoes for what must seem like a very long time, yet the journey has only scratched the surface of what there is to know. Volcanoes are endlessly fascinating. Each one is unique. Each eruption tells a story. Each fact leads to more questions. Scientists will be studying volcanoes for as long as science exists. But tonight, you do not need to learn anything more. You have done enough. The facts we have shared are settling into your mind like ash settling on a quiet landscape. Some will remain. Others will drift away into the peaceful darkness of sleep. Either way, you have traveled far, and now it is time to rest. And so we come to the end of our journey. We have traveled through over 100 remarkable facts about volcanoes, from the fires of ancient mythology to the cutting edge of modern science, from the depths of the ocean floor to the peaks of the solar system's tallest mountains, from catastrophic eruptions that changed history to the quiet volcanic processes that make life on Earth possible. Volcanoes remind us that our planet is alive, that change is constant, that even the most solid-seeming ground is part of a dynamic system that has been evolving for billions of years. As you drift here at the edge of sleep, you might imagine yourself resting on a volcanic slope. The rock beneath you still holds a gentle warmth from the Earth's interior. The stars are bright above. The air is still and calm. The eruption is over. What remains is peace. The volcano will still be here when you wake. The Earth will continue its slow transformation. Mountains will rise and fall over millions of years. Islands will emerge from the sea and eventually sink beneath the waves. New volcanoes will be born and old ones will fall silent. But tonight, none of that requires your attention. Tonight, there is only rest. Sleep well, rest well, and may your dreams be peaceful. Good night.